Hello, everyone. So this is the beginning of video 14. So our first video for week 6, I guess this is, or maybe week 7, after the test. And so we're now going to begin this week to talk about some applications of calculus in more detail, namely using what we did the week before the test on finding local max, local min, to optimize, to solve optimization problems. Meaning, say we understand we want to minimize the cost of making something, or we want to minimize the cost of building something, or the amount of material involved in building something. And that this is a problem depending on the specifics that can be approached using the techniques that we learned about maximizing or minimizing functions. So, I mean, just to recall a bit, hopefully you practice this for the test, so it shouldn't be too unfamiliar. It wasn't too long ago. So if we had some kind of function, I'm just drawing an example of a curve like that, we learn techniques, right, to find points here, A and B, right, where the function was reached a maximum and the function reached a minimum using calculus, right? So we found the max min of a function y equals fx by doing the following. By first finding the points x where f prime at x, where the derivative was 0, right? So we noticed in our discussions that if you are at like a hilltop or bottom of a valley, the tangent line must be flat there, right? So you have to have a 0 derivative. The tangent has 0 slope, it's a flat line. And then to figure out whether not every point where there was 0 slope was a min or a max, right? We saw that with the cubic curve, right? You could have a point where the curve rises, becomes flat, and keeps rising, right? So to determine out of these points which ones were min and max, we had 2 tests. We had the first derivative test and the second derivative test. And I won't go through exactly what they were again, but you can go back and look if you forgot. But you can just, and either of them can apply here, and just remember what they are and pick the one you like the most to use. Okay, so then we determined amongst the points we found in part 1, in part 1 here, in step 1, say, which points were min max using either the first derivative test or the second derivative test. And like I said, I won't go through what these are again, but you can pick which one you like the best. I guess it also depends a little on the circumstances. The first derivative test, remember, you compute the first derivative, which you've already done in step 1, and then you have to check the sign of the first derivative around the point where the first derivative is 0, right? Around that point you're thinking about. And, for example, if the first derivative is positive to the left of the point, then the function is increasing up to the point, flat there, and if it's negative after, it's decreasing. So positive first derivative to negative first derivative is a max, etc. But that's a bit tedious because checking the sign of different factors of a function can be annoying, and I built that table, and it takes some time. If the second derivative is easy to compute, which it often is in these kind of functions we'll be dealing with, then you can use a second derivative test. So you compute the second derivative and you just check if the second derivative is positive at the point or if it's negative at the point. If the second derivative is positive at the point, then the graph is bending up at that point, so it's a min. And if it's negative at the point, the second derivative is negative at the point, graph is bending down, so it's a max, etc. If the second derivative happens to be 0 at the point, then you have no choice. You have to use the first derivative test. Now, that's just kind of a review of what we've done. Now we're going to, and what we want to apply to these problems. The difficulty I find with these problems isn't just repeating these steps. We've done this many times. These problems don't, they're not like in the form where it's like, oh, here's a function, find the max and min like we did before the test. They come, what we're going to see is we're going to get a real world description of a problem. And from this real world description of a problem, we have to build equations, like model equations using some geometry or some numbers theory. And then from those equations, which we construct, apply these steps. And that's what's hard. So it's like these two things we discussed earlier, are part of a multi-step process to solve these real world optimization problems. And I think the tricky thing is like with those physics problems we did several weeks ago, is going from the English word problem, building the equations from there, and then applying the calculus to get the conclusions that we need. So, but for these real life problems, for these real world problems, we aren't just given a function f of x. Although a few of them on the homework still do this. And I don't know. That's so that kind of, those problems are a lot like the ones you've seen before. But we have to find this function. We have to construct this function. From real world information. Okay, so let me give you an example. And the problem, somehow, like there's a general procedure for doing this, but it varies a lot per the type of problem you're looking at, how to construct these equations from real world information. Okay, so let me give you an example. And then maybe I'll kind of make some general comments, but it's something, again, like you have to do there's no general catch-all way of doing these. You have to kind of do it in each question in some sense. So example 1. Find two numbers such that their difference is 100 and their product is minimal. Okay, so this is exactly what I was kind of talking about. We're not given a function y equals fx and told go find the minimum and maximum of this function. We're saying, something much more ephemeral in some sense. Find two abstract numbers whose difference is 100 and their product is, and minimize their product, right? So the first step, and again, like I said, there's some kind of very general things you do, but is introduce variables. For the quantity to be minimized, or in other cases maximized, but in this case we're kind of just minimizing it. So that's step 1. Okay, so what I'll do is let the two numbers be x and y. Okay. Now, the second step is write down the equation in terms of these variables you've introduced. Write down the function you want to minimize. Now, this function will be a function of these two variables you've introduced, and we'll have to deal with that because we don't know in this class how to deal with functions of two variables. But that's okay. There's going to be a way around that. So step 2, write. Maybe I should do this. Oh, I can just put it in a box or put it in blue, different color for the steps. So step 2, write down the function that you want to minimize in terms of the variables you introduced in step 1. Okay, this will be a function in general. This will be a function of at least two variables. In this case, it's exactly 2, but there could be more. In most of the problems I think you guys do, there are always only 2. But if I look through the homework, I think, but it could be in applications a little bit more. In general, this function will be a function of at least 2 variables. Okay, so let's go back up here. Okay, so find 2 numbers such that their difference is 100 and their product is minimal. So the 2 numbers, we're calling them x and y. What's the function that we want to minimize? It's their product, right? So we want to minimize the product of these 2 numbers. And sometimes when you read these things, it's nice to highlight what you want to minimize, right? In the question. So the function we want to minimize in terms of the variables we've introduced is the following. Is f is equal to the product of the 2 numbers x and y, right? So those are the 2 numbers we introduced, and that's what we want to minimize. The quantity we want to minimize, x times y. Okay, now this is a function of 2 variables. We don't know the calculus function of 2 variables is calc 3. It's a very, very difficult thing. But there's information in these problems. There's information in these problems that allows you to express one variable in terms of the other. And that will allow us to rewrite this equation in terms of a function of one variable. So the third step, and this is the most important, I think. Step 3, oh, I'm supposed to be writing steps in blue. Step 3, identify the constraint information. I'll explain what that means. On the variables in the problem, which will allow you to express one of the variables in terms of the other. Thereby allowing you to express the function in step 2 as a function of one variable. Okay, so we have this function of 2 variables. I claim there's some information in the problem, a constraint on these variables, something that they have to satisfy, that these two numbers, some other thing these two numbers have to satisfy, that will allow us to express either x or y in terms of the other. And in doing so, we can use that expression to rewrite this function in the second step in terms of only x or only y if we want. We have to pick, there's some choices to pick which one you want to do. So let's go back to the statement of the question and see if we can identify the constraint. So find two numbers such that, oh, their difference is 100 and their product is minimal. So these two numbers have to have the property that their difference is 100. And that relates these two numbers, x and y. That gives us a constraint on these variables, x and y. So the problem requires that the difference of these two numbers is 100. And so from this information, we can find a constraint equation. Sorry. Relating the two variables. So the difference of these two numbers is 100, means that x minus y equals 100. So that's our constraint. This is the constraint. So now, so let me just summarize. So now we have the equations, right? We have, because it's way up on the pad, so I'll rewrite them. So we have the two equations. F equals x times y, which is the product we want to minimize, and x minus y equals 100, right? That these two numbers, their difference must be 100. We want to minimize their product. Now, like I said, this constraint equation allows us to say solve for x in terms of y. X is 100 plus y, right? If you just rearrange this constraint equation, we can solve for x in terms of y. This expression for x can then be substituted into the equation for the product, the function of the product, which is a function of two variables, to get an expression for the product that only involves the variable y. So now, solve the constraint equation for x. And substitute the expression into the formula for f to obtain, I don't need a comma there, to obtain an expression for f only in terms of the variable y. Okay, let's do it. So we have, if we put this expression right into f, we get f as a function of y is 100 plus y times y. And now this product of these two numbers is expressed as a function of a single variable. And we know how to minimize that function using the techniques we talked about before the test, right? So this is the last step. I guess it's step 4. Minimize the function star, the function f of y, sorry, I don't call it star, haven't given a name yet, the function f of y, using the techniques we discussed at the beginning of the lecture. First derivative test, etc. Okay, so let's do that. And this is the final step. So I don't like, we want to compute the derivative of this expression f of y. I don't like using the product rule. So I'm going to expand it, simplify it a bit, and you'll see it's much easier. We can just use the power rule at that point. So I'm going to simplify f of y slightly. And if you do that, you get f of y equals y squared plus 100y. And so now find points such that f prime at y equals 0. So f prime at y equals 2y plus 100, and set f prime at y equal to 0 and solve the guy and see what we get. So we get 0 equals 2y plus 100. And so if my algebra is any good on today, this Monday, I would get that y equals minus 50, right? So now what I want to do, so now we have to figure out, do we want to do the first derivative test or do we want to do the second derivative test? The second derivative is very easy here. So let's do the second derivative test. So f double prime at y is, where did f prime go? Oh, there it is. It's just 2, which is always positive, right? So the graph is bending up always, right? And so this point you found where the first derivative is 0 is a min, which is what we wanted. So f double prime at minus 50 is greater than 0, and by the second derivative test, y equals minus 50 is a minimum. Now we have to, so now we found the one variable and now we have to find x, because you wanted, remember the question wanted 2 numbers. We're not quite done. We've done all the hard stuff, but where did it go? But we need to find x, right? So we found the y and now we need to find the x. So the last step is to go back, and this doesn't always have to be done, but sometimes it does, is go back to the constraint equation and solve for the other variable, the value of the other variable at the minimum. So if we do this, so what was that? And I lost the constraint equation. Where did it go? There it is. Let me just, oops, copy this guy. So we had x. So when y equals minus 50, right, x is equal to 50. So the 2 numbers we're looking for are x equals 50 and y equals minus 50. And that minimum, their difference is 100, right? And the product is a minimum. Okay, so those are all the steps. I mean, these are kind of involved problems. There's several steps. So we'll do several for practice, okay? Okay, now the reason these problems get kind of tricky are that many of them involve geometry. And so this one was, I think, one of the easier problems because it just involved like products of numbers and difference of numbers. You didn't have to draw a geometrical figure and then kind of translate information from that figure to mathematics, which is an extra step. So in other words, in this problem, where was it here? Step 2, right? So in step 2 here, where we had to write down the function that we wanted to minimize, it was just the product of the two numbers x and y, right? And that didn't involve any geometry. We just take the product of two numbers. There's no geometry there. But many of these functions you want to minimize have to do with something geometric. And so then in this step, there's the added complexity of drawing a kind of diagram that you associate with the variables, and then using geometry to write down this function that you want to minimize or maximize. So in the next, and it's kind of, I should say that part, the diagram part's kind of tied in with step 1 and step 2, right? So the next several problems are all of this nature. So let's dive in. Okay, so I'll use this. So question 2. So I should just say now optimization problems. Involving geometry. Problem 2. So you want to build a rectangular fenced area with one side being your house. Find the max area you can enclose if you only have 100 feet of fencing. What is the length you would make the side opposite your house? Okay, so this is a kind of a much more involved problem. So let's read it carefully and identify what is it we have to maximize. Eventually, we need to identify the constraint, etc. So we want to build a rectangular fenced area with one side being our home, and we want to maximize that area, right? And that under the constraint, right, that we have 100 foot of fencing available to do this. And then it's asking us for the maximum area, what is the length of the fence opposite the side of the house? But that we'll answer at the end, so we'll get to it. Okay, so the first step, I guess I'm supposed to do this be consistent in that nice blue color. Introduce variables, right? For the quantities, for the quantities involved. Okay, now this case, in the previous problem, we had just two numbers whose product we wanted to be a minimum and so forth. And that just required like calling the numbers x and y. Now, in this case, we have like a geometric situation where we're trying to fence in a rectangular area. And for that, we really need to draw a diagram to be able to see the geometry. That's what I was saying a minute ago. So, and this, to introduce these variables and to figure out how to write down the function that we need to maximize, namely the area of some rectangle, we need to draw a diagram. So since the quantities involved are geometric, in this problem, we need to draw a diagram to introduce variables. And then to write down the geometric function, the geometric quantity, we seek to maximize in this case, not minimize. Okay, so here's the diagram. I'm not, again, you know, I'm not a good artiste, but so say the home is here. It's your house. The house will be this side. So this will be house. So one side, there's a rectangular area, one side's the house. And ultimately, we want to know, right, the opposite, the length of the fence opposite the house. So I'll call this x, this length x. So it's the length of the fence opposite the house. And it's a rectangle, so these sides are both y, right? So, and you know, I don't know, let's make it into a fence, you know, if you want to be a little artistic here, but don't go overboard. Okay, so there's our backyard that we want to fence in, and the house kind of, you know, like I said, not a good artist here. The house should connect with the fence on both sides. I'm not even trying to draw the house. It's just going to be a box house. Okay, and of course the length of this side is also x, right? Whatever the length of the house happens to be. All right, so the area, so that's step one. Step two is to write down the function we want to maximize. So step two, right? Okay, so the area is we wanted to maximize the area of this yard, right? So A is equal to area of a rectangle is just x times y. So again, it's a similar formula to the one we had in the first problem, but coming from a different perspective, a geometric perspective, rather than a number theoretic perspective, right? So this is just the area of a rectangle. Okay, again, that's a function of two variables, right? It's a function of, you know, the length of the yard, and it's a function of the width here of the house. All right, and so now step three is identify the constraint. And use the constraint to rewrite function in step two as a function of one variable. Okay, so the constraint was, we go back up, we go back up to the problem. The constraint here I've highlighted in this, underlined in this dark blue, right? The constraint is that you only have 100 feet of fencing, right? You only have 100 feet of fencing. So I'll keep the diagram up there if I can, or I can kind of maybe. This is the one disadvantage of not having a blackboard, right? Is that if I had several blackboards, all this stuff would be visible at the same time, and because it's not, I kind of have to. That's fine. I kind of have to keep repeating things, rewriting things, so don't scroll up. So this length is x2. Okay, so I can clean that up here. Okay, so the constraint is only have 100 feet of fencing. Okay, so what does that mean in terms of the relating the variables x and y, right? So 100 feet of, so how much fencing do we have? Well, the side that's the house isn't fenced. You're not gonna like fence in your house and not be able to go to the backyard. That would be just crazy. So the amount of fencing we actually have here in this picture, so I can get rid of the x here. The amount of fencing we actually have is y plus x plus y. Like the fence is y, x plus y. The house, you don't fence in your back of your house. Okay, that's just nuts. I don't know why you'd ever do that. So the fencing is x plus 2y equals 100. That's the constraint equation. Okay, and now I didn't make much of a do of this last time because it didn't really matter how we did it. So last time I solved for x in terms of y, right? I could have done the other way in the last problem. I could have solved for y in terms of x. That would have been just as legit. But here, you really want to solve for y in terms of x, because in the end, I mean, it doesn't really matter, but you'll be able to skip a step. Because what you want to know, what the problem's asking for is what this length x actually is that causes the maximum. It doesn't care about the length y. So in the end, it wants the x value. So you'll save yourself a little bit of time here if you solve for y in terms of x and get a function in terms of x instead of y, like we did last time. If you go the other way, it's okay. You'll just have to go back to the constraint equation like we did in the end of the last problem. But anyways, I'll do it this way because it's a little more efficient. Okay, so since the problem asks for the x value in the end, the x value that maximizes the area we can save some time by solving for y in terms of x now. So if we do that, we would get 2y equals 100 minus x. So y equals 100 minus x divided by 2. So this is 50 minus x over 2. Clean that up a bit. And now we substitute this expression for y into the function f equals x times, or the area function, so capital A for area, is x times y, to obtain a function of only x. X, so let's do that. So we get area times x is x times 50 minus x over 2. And simplify. Oh, so that's the end of step 3. So that's our function in terms of x. Get carried away. Now step 4 is find the maximum using calculus. So we have a at x, and again, simplify this a bit so you don't have to use the product rule to construct the derivative. All right, so you have a at x is 50x minus x squared over 2. So find points. Where a prime at x is equal to 0. So you get a prime at x equals 50 minus 2x over 2 is 50 minus x, and solve. A prime at x equals 0. This is just solving. This is very, very easy. This is just solving 50 minus x equals 0. And that's the same thing as saying x equals 50. And now we need to check that this is that this actually maximizes the area using the first or second derivative test. I'll again go with the second derivative test here because it's very easy. So finally, we check that this maximizes the area using either the first or second derivative test. Like I said, I will use the second derivative test. So the area is here, right? It's 50 minus x. We had a prime at x is 50 minus x. So the second derivative is just minus 1. So a prime at 50 is minus 1, which is negative. The second derivative is negative. This is actually a parabola that's just opening down. The graph is always bending down. So the graph is always bending down. That means the point where you have a flat tangent is a maximum. It feels like I'm doing the YMCA here. But so if your graph is bending down, always the point with the flat tangent is a maximum. So x equals 50 feet maximizes the area of our yard. Okay, so I will stop there for now, this first video. I will shortly make a second video where we do some more complicated problems. So we'll do a few more things with rectangles because they're fun, but then we need to do something with three-dimensional things, cubes, which are a little trickier, right? And cubes and rectangular prisms and things like that, which are a little trickier, but we will keep practicing. And I'll pick up the pace a bit. So I wanted to do these first two problems very, very slowly, so you get a sense of how to think about it and how to lay it out, the steps. I will go through these steps much more quickly in the next batch. All right, thanks for tuning in.